All right, so this video is on the probability of compound events. So up until this point, anytime that we've talked about probability, we really talked about the probability of just one event. That means just one thing is happening. There might have been multiple conditions, but there's only one event that we're trying to evaluate. So simple probability, you all know that's just the probability of the number of given things that fit the criteria over the total number of things. The probability of so we've done this before, is when you have two conditions that you're talking about being met. So for example, if you're talking about the probability of getting something that is a black card and is a 2, we're really just talking about these two cards, right? So that's like 2 out of 52. The probability of so this is where or gets just a little bit different. Or we have to minus the overlap. So when we say the probability of getting a black card or a 2, on that one, let me erase what we have here. All right, or a 2. So black card would be all of these. So that's 26 cards, right? Or a 2, there's 4 2s. So plus 4. And then we have to subtract the overlap because this, where it's black and 2, we're double counting that, so we subtract that 2. Still, that's going to be out of 52 because there's 52 total cards. But again, on this, we're talking about if we draw one card. So when we say these are all single events, this is just one draw. Today, what I want to talk about is compound events, and that's when we're talking about multiple draws or whatever it is you're talking about. You're not just talking about one card, but drawing multiple times over and over and over again. Okay, so here's an example. What if they ask you to find the probability of rolling a 6 and then an even number? Okay, so here we're talking about rolling a die 2 different times. So it's a single die, not 2 rolled at the same time, but a single die that you're rolling 2 different times. So in this we have 2 events. And what we're going to do, there's this rule called the multiplication rule, and what you do here is you multiply the probabilities for each event to come up with the final probability. So we've got 2 events, so I'm going to do the probability of one times the probability of another, and that will give me my final probability in the end. So first, the probability to roll a 6. Well, a die, if we're talking about just a general die, it has 6 sides, so that's going to be 1 out of 6. And then we roll an even number. Well, if a die has 1, 2, 3, 4, 5, 6 as the options, there are 3 options that are even. Now, this is not saying, right, again, this is not an and or an or. I'm talking about rolling the die 2 different times. So I've already talked about the first event. Now I'm talking completely separately about the second event where we're going to roll an even number. So on that one, it's 3 out of 6, or 1/2 is the probability of rolling an even number. So again, this is 2 different rolls. This is roll number 1 and roll number 2. And so we can multiply those together to get the probability of that happening if we rolled the die 2 times would be 1/12. And that's for 2 events. All right. Now on this example specifically, this shows something called independence, which means that these 2 events don't change or have any dictation on another. So for instance, you rolling a 6 on the first one doesn't change the number of sides there are on the dice. When you pick the dice back up to roll it again, there's still 6 sides. So you still have the option to roll a 2, a 4, or a 6, right? That's how we have this 1/2. So independence is when the 2 events don't have any impact on the other. So let me show you something that's called dependence, which is obviously the opposite, so you can see kind of how those relate to it. All right, so in compound events, it doesn't necessarily just have to be 2 things. It can be any number of events above 1. So in this example, they're asking the probability of drawing 3 hearts. I'm really sorry, my writing is so sloppy. I don't have my good pen. Okay, so in this one, and let me be specific. Probability of drawing 3 hearts without replacing the card, because that's what's going to make this problem different. So if we're talking about not replacing the card, The first time we draw, the hearts here, right, in here, there's 13 hearts out of 52. So I'm just going to make this, even though I know that reduces, I'm going to write it like this. I'm drawing 3 events, so I'm going to do 1, the second event, times the third event. So the first time I draw, I've got 13 hearts to choose from and 52 cards. Now, if I'm trying to draw 3 hearts, I have to assume that I already drew one the first time. So the next time when I go to draw hearts, I don't have 13 to choose from anymore. It doesn't matter which heart I've drawn. Now I only have 12 hearts to choose from. And the same thing is going to happen to the total number of deck. I no longer have 52 cards in my deck. I only have 51 cards. All right, and then we're going to think, well, that same thing is going to happen again. Now if I've drawn a second heart, I no longer have 12 hearts to choose from, but I have 11. And I no longer have 51 cards in the deck. I now have 50. So this shows you, and then, you would multiply that and you would get some crazy large numbers. But this whole concept shows you, this is an example called dependence, because what you do affects what happens the next time. D and C. All right, so this is an example of dependence. Notice that on dependence, it's really like this denominator is changing every time. And sometimes the numerator as well, because you have less options to choose from. What you've done, again, like I said, what you've done the first time changes the probability of what's going to happen in subsequent events. Whereas if you think back about that dice problem, rolling that no matter what you rolled the first time, the dice still has 6 sides. All right, so here's just a quick list of common independent and dependent events. Dice, always going to be independent because rolling 1 does not affect rolling whatever happens in a subsequent event. The same for coins. You can flip tails, and when you pick that coin up, you still have the same 2 options that you had the first time. Cards with replacement. So, for example, if somebody's doing some crazy magic trick, right, and you pull a card and you put it back in the deck, as soon as you put it back, the odds are back to what they were the first time, right? The probability is still the same because you put it back, so now there's still those 52 cards. Dependent would be like what we just did, cards without replacement. So once you take it out, you're changing the probabilities that exist. Bingo is another kind of dependent one, because like if you think about when you're playing bingo, if you pull out, B12, you don't put that back in. Even if you did put it back in, that would be dumb. That's not how you play bingo, because then you wouldn't be able to cross that off anymore. So bingo is an example of dependent, because once you pull it out, the number that's in there goes down. There are definitely more to this list. These are just some common ones that maybe you would write down just to kind of have in your back pocket for when we start looking at some probabilities together.